These experiments are more complicated than simple band structure, and the effect of this on localization physics is not totally known. David knows a little bit about this. He's included in a recent paper. Lawrence Sanchez Palencia has worked on this somewhat and understands some things about this. But certainly, what happens to these states in the presence of interactions is something which no one really understands. It's a really big open question. I think just Chris Woolley has started to work on it somewhat. Okay, so moving along, what happens when you add disorder to this? So this is now specific to my experiment. So far, everything's been really generic, or experiments in my group. So in my group, what we do is we have optical lattice that's cubic. We do this by bringing in 3 pairs of optical lattice beams. Okay, so there's a pair here, a pair here, a pair here. They're orthogonal, makes a cubic lattice. And we also bring in optical speckle from one direction and focus it down onto the atoms. Okay, so we have an optical lattice potential. Its potential depth is, sorry, that freaked me out for a minute. Okay, it's like fire alarm. All right. The optical lattice potentials can be adjusted by the red laser. There's speckle, which can be adjusted by the green laser intensity, and they add together to make a disordered lattice. Those two potentials are independent potentials. They just add. They're independently adjustable optical lattice. So this is about as much as I'm going to talk about the experiments in my group. We do a lot of experiments and have done a lot of experiments using these 3D disordered lattices that realize 3D disordered Hubbard models. By working with David Sepperly's group at Illinois, we know the distribution of Hubbard parameters now, because of course, in a disordered lattice, the tunneling and interaction energies now are disordered, and there's a distribution of energies which are present. These are the probability distributions. And there's a site energy, which I didn't write down before, which you also have to keep track of, which Vadim wrote down, somewhere hidden behind one of these boards, and that's also disordered. So in general, these experiments have all types of disorder present, but we know the distributions of these parameters.
What are the blue and red there? Are they occupied and unoccupied?
No, these two curves, that's, so.
No, I meant over on the left.
So I'm just drawing a cartoon. Those are the atoms. This is like we're working with fermions, and those are 2 different hyperfine states of atoms, which would be like spin up and spin down. Yeah, that's my cartoon. My group does experiments with both fermions and bosons and lattices like this. And other groups do too, although I think I'm the only group still working in 3D disordered lattices. But other people have worked in 2D disordered lattices, which I'll mention in a minute, and 1D disordered lattices as well. Something which hasn't come up yet is a mobility edge. And I'll mention this tomorrow, I'm sure Vadim will talk about this too. In 3D disordered systems, there is something called a mobility edge. It's an energy scale that separates localized from unlocalized states. And now we know this mobility edge for single particles in this 3D disordered lattice. What happens is you turn on disorder, localized states creep in from the top and bottom of the band. And Sebastiano Pallotti has calculated this now, and this is where the mobility edge is for different disorder strengths for the single particle problem. So this is also sort of known now for these 3D disordered lattices, and the details here aren't very important, but there's the paper and the reference if you want to learn more about it.
Ryan, you got a question right here.
Yes, thank you. Sorry, I'm running out of caffeine. Yeah. Yeah.
So if you have these atoms, these caps, and
Yeah.
if the cap is very high,
Right.
then there will be very little tunneling,
Mm-hmm.
and also the overlap will be very small, so the interaction is very small too. So if it seems like you might be able to write U of I, the interaction strength as a function of tunneling, or if they're very related, because they look at
Okay, so that's a great question. So let me talk a little bit more about how the interaction energy and tunneling work, and I'll sketch a picture up here in a minute. So first of all, yes, we can tune the tunneling by tuning the size of those potential barriers, right? The size of that optical lattice potential. The tunneling can be big or it can be small. The single particle states are always delocalized states. They're always block waves in that periodic potential, always. That's the solution to Schrodinger's equation. And with single particles, we can really see all that physics. And with spin polarized fermions, which cannot interact with each other, we can see that all work out just right. Okay, so for strong lattices, in fact, because the interactions are only between particles on the same site, for strong lattices, the interactions are stronger than for weak lattices. Okay, so I didn't really draw that in my cartoon, shame on me. If these were fermions, what can happen is you can have one blue atom and one red atom on the same site, and that's this interaction term there. Okay? The interactions between atoms on different sites is really tiny, itsy bitsy. Always, for any of the experiments. Now, so if I was, just to show you a little bit what happens here, so if I plot the tunneling energy versus lattice depth, you know, it goes down very quickly, kind of like an exponential. All right? And if I tune the lattice depth, the interactions go up kind of like the fourth power with, kind of like that with lattice depth. Okay, so they tune together to some extent if I tune just the lattice depth. Okay, so these dashed lines here are the non-disordered values for this lattice. So for example, if I crank the lattice depth up, this line here would move to smaller values, and this line would move to bigger values. Okay, and then the disorder comes in and broadens those tunneling interaction energies and turns them into distributions. Does that make sense? Kinda? Shaking your head like you maybe don't believe me, but we could talk more about it. Any other questions? Okay. Yes, this is a detail, but for those of you who are experts, mobility edge trajectory is known now for these lattices. There's a picture of it. We'll come back to that tomorrow. Okay, so let me talk about some other people's experiments. And their names are cut off from the bottom, so these are important. Another disorder technique. Okay, so that was all about, so far, that was all about speckle disorder. So how speckle disorder is made and how it's used in experiments, 1D, 2D, 3D, and with optical lattices. All right, that was all speckle. It's the most common tool for making disorder in experiments. It's the most widely employed. All right, so now I'm going to talk about two other methods, and then which are optical. Another method which has recently been used by Emmanuel Bloch's group is so-called projected disorder. So in these experiments, an optical lattice is formed for atoms trapped in a plane. So there's a 2D optical lattice here. Atoms are trapped in a plane. And disorder is created here where it's controllable disorder. So you can kind of think of it as a diffuser where you control the shape of the diffuser. It's really the formable mirror array where light is bounced off of it. And you can think about it like a diffuser where you can control the shape of it. So you get to decide, based on a computer controlling this thing, where all the bright and dark regions here are in this disorder. So light's bounced off of this thing, collected by a lens, which is not shown, and focused down onto these atoms which are trapped in this plane. And so it's more controllable or designer disorder. It's a really neat and beautiful technique, which so far one group has employed. And I'll talk about what they observed with that tomorrow. Okay, so that's what we call projected disorder. It's like speckle disorder, but it's controllable. Okay, so in principle, within limits, you can sort of make the intensity landscape and the potential landscape look however you like. And so you can see here they made something different than speckle. In speckle, the probability distribution of different disorders would be exponential. Here they made something which was Gaussian, right? Which is not speckled. All right? That's another type of optical disorder. Another type of disorder, quasi-disorder that people make, and a lot of experiments have relied on, is made using incommensurate lattices. All right, so one type of disorder, another type of disorder. This is many groups, and I'll talk more about this tomorrow. This is a plot I stole from one of Nguccio's papers. Here what's done is two optical lattices are superimposed where the lattice period, well, the wavelength used to make the lattices, and hence the lattice periods, are incommensurate. They're not related by they're related by an irrational number. All right, so if you look at this and you don't look too closely, it looks kind of like it's disordered, right? Because you've got one lattice with another one with a different and incommensurate period added together. So taking a finite sample of this in space like that looks like it's disordered. Technically, this realizes what's called the Aubrey-Andre Hamiltonian for a single particle. All right, so I'm using Nguccio's notation here. He likes J for tunneling. And I wrote this down kind of how Vadim wrote it down, where there's a tunneling term in this lattice, the height from site to site, and there's a disorder energy on each site, which is controlled by the incommensurate lattice. So typically you have one strong lattice here, made by lambda 1, and then a weak lattice made by lambda 2, and that's taken into account in terms of this disorder here. And this phase controls the phase offset between the two lattices which are adding together here. All right, but of course, it's really just incommensurate lattices, so this is not really random in some sense.
So the data, so they observe localization for very large data. So that means how do you resolve it from classical?
Yeah, so I'll talk more about that tomorrow. Because theory is relatively tractable on this system, they sort of know what's going on. And they know there's a quantum localization transition at delta equals 2j.
Delta equal to 2j in this.
Pardon me?
Yeah, so of the order of delta equal to 2j, localization. Right?
I'm just having a hard time hearing, but I'm getting old.
So for delta goes to let's say 2j plus 1.
Yeah.
So they
Yeah.
don't see any localization.
Yeah. Okay. So there's a lot of there's a lot that's been written about this, and I'll talk more about it tomorrow. Yes, and in fact, there was confusion even about early results that were not localization, when people thought it was localization. All right. I'm not going to go into a lot of that, but I'll mention it tomorrow. So phenomena that have been observed here, I'll talk more about tomorrow. Yeah, but there is a localization transition here at delta equals 2j, but it's complicated. All right. Let me also just mention that you should be cautious. There are papers that have called this disorder. It's not disorder in the usual sense. So Dominic Schnabel, whose work I'll mention in a minute here, looked carefully at this kind of disorder, or quasi-disorder, incommensurate lattices, versus other kinds of disorder. And he pointed out, what's that? Yeah.
What the beta is? What's the beta?
Yeah, beta is, sorry, I was not careful. Beta is a ratio of wavelengths.
Oh.
Yeah, or periods. Right, and it's not really random, it's deterministic, because you're just adding one lattice to another lattice, and there's some phase offset between them and some.
Okay, so this spectrum is only applicable for some special ratio of this beta, or it's a
This-
general result?
What's that?
I mean, this spectrum, the second term,
This thing.
yeah, that kind of spectrum is only applicable for some special.
No, I
specific
mean, this is always
spectrum.
true. This is just saying you have some strong thing, and you're adding some weak perturbation to it, and this is just the second weak lattice, or just shifting the energy of each site.
Okay.
But it's periodic in space, because it just comes from a periodic potential, which is what this is periodic in space, right?
Yeah.
Yeah, so I mean, to be careful, this is not really disorder, but it's been used as kind of a model of disorder by many groups. Because if you don't look too carefully, it kind of looks disordered,
Okay.
right? But it's not. This is just some other spatially varying potential.
Okay.
But to be inclusive, this is one thing people have looked at, and looked at as a kind of disorder. Okay? And especially if you make this irrational, if you don't look too closely, it's hard to tell it's not disordered. Okay, but Dominic Schnabel has pointed out that if you look at various correlations and histograms of this disorder, it's not really disordered. It's actually perfectly correlated. All right.
Sir,
Yeah.
experiment, can you really make beta to be rational?
You get well, it's not perfectly, and you can't measure it that. You can measure it, as well as you can measure it. You can measure wavelengths part per trillion. At that level, you could try to make it irrational.
Excuse me. Sorry.
Yeah.
The previous slide.
Yeah.
So can this method create optical lattice in 2 dimensions or 3 dimensions?
Yeah, you could do this you could do incommensurate lattices in more than 1 dimension. But so far, people have only used them in 1D. Okay? And I'd say people are moving away from this as a technique. More groups are moving towards speckle or projected disorder. But this is something a lot of people have done experiments with, and I think it's important to understand what it is and then what role it played in our understanding of localization in these systems. Yeah, Fadim.
If it doesn't stretch it too far, is there anything, can you tell us what's known in 2 and 3 dimensions probably to measure localization?
No, I can't. I don't know how much is known, actually. I have no idea what's known and what's not known.
So this disorder is the short range or long range disorder?
Well, it's not really disorder,
Okay.
right?
Yeah, but
It's 2 lattices added together. with incommensurate periods.
Yeah, but I mean, if you look at a larger scale, like
Yeah.
I mean, the physics, the quantities should be looks like a long range order.
Yeah, so there's a lot of discussion of this in theory literature, and I don't know everything about it. I'll tell you about some results from it tomorrow.
Okay.
Yeah. This is a topic I know less about because my group is not using commensurate lattices. Okay, so I'm trying to summarize here work by a lot of different groups. Okay. Right, so Dominic Schnabel at Stony Brook has pointed out it's not disordered in the usual sense, and that's important to keep in mind. All right, one last thing I want to talk about, and I'll have this almost here on time. It's a very unique experiment using impurity disorder. This is a beautiful experiment where impurity disorder was compared with incommensurate lattices, and this experiment does not get enough love. This was really great and important, I think. So in Dominic Schnabel's group, he did measurements where he had impurity disorder, where the disorder came from atoms, which were in a lattice, but experienced a different lattice than the atoms that were sort of the lattice atoms. Okay, I'm just thinking for a minute here if I got this picture backwards. No. Okay, so what he did was he used a very special lattice called a state-dependent lattice, which I'll explain more about in a minute, where atoms in different MF states experience different lattice potential depths. And he added in these impurity atoms here, which experience a different lattice depth than these blue atoms, which are the atoms they kind of measure the properties of. And through that mean field shift, through that collision interaction, that contact potential, those impurity atoms, wherever they lined up with the site, shifted the energy on that site. Okay? And because those impurity atoms were sprinkled randomly throughout the gas, it created random disorder. Beautiful, beautiful experiment that needs to be some experiment that I've encouraged several young people to follow up on. So how does this work? Well, there's a reason I showed you this horrible diagram, which AMO people love, of course. To me, this is beautiful. But I showed you what a real atom looks like. This is rubidium-87, which is the atom Schnabel's group used, where we have an electronic ground state and the two excited states split by the fine structure. Here's a hyperfine splitting down here. Here's all the different MF levels. And I told you, and I didn't derive this, and I'm not going to derive this, although I know how. This is the dipole potential for a real atom like this, where there are multiple terms, one for the transition to the P3 half state, one from the transition to the P1 half state. And these terms are actually polarization dependent. Okay, so there's a number here, which is the polarization of the laser beam, -1, 0 for pi or linear polarization, +1 for right circular. Okay, and these are polarizations in what's called atomic basis, which is defined by a magnetic field. And notice also they're multiplied by an MF, by the MF level of the atom, which remember we control and we select in our experiments. So one thing you'll notice about this is that there's some tricky things to do. First of all, if the light is very far detuned compared to these transitions, then these two detunings are the same, and this polarization dependence and MF dependence cancels away. Okay, but if you're not too far detuned, then this polarization and MF dependence can be maintained and used. And what that means is necessarily the reason not a lot of people have done these experiments is because there's going to be more light scattering or spontaneous scattering from these excited states because you're not too far detuned from them. But that's okay. People can still do things. All right, so how does this help you out? Well, notice something here. So if you have an MF equals 0 atom, it only cares about intensity gradients. That's what makes a potential or a trap or a lattice for them. But if you have, because M is 0, so these terms disappear. If you have atoms that are MF equals, say, -1, then they can be affected by polarization gradients in space. And that's exactly how Schnabel did those experiments. So this is an extreme version of that experiment. What you can do is you can make what's called a Lin-perp-Lin lattice in the parlance of atomic physics, where you take two laser beams and shoot them at each other, but they have orthogonal polarizations. So if they have orthogonal polarizations, then the intensity is uniform. And so an M equals 0 atoms will experience no potential, except for an overall trap, which is always present. But there are intensity gradients that are present. So if a magnetic field lies along that axis of the laser beams, then you can write down the electric field as actually a superposition of sigma plus and sigma minus light, which are out of phase. So if you stick an M equals -1 atom in there, it will actually experience a lattice potential as it moves in space. And so you can trap atoms together that experience different lattice potentials. You can make